Hello, chemists. It's me again. Hey, we're going to continue studying kinetics, and this little video is going to be on how to do the calculations once you know whether it's zero order, first order, or second order. So we're going to ask the graphs, and then we're going to use the data that it provides. So I have some example problems right here. All right. So I went into the lab and I got some data. And of course, it's really good looking data, it'd be almost perfect. But here's what I got. I manipulated it just like I showed you in the last video, and here's the graphs that it gave me. All right, what am I asking the graph? Right here. What am I asking the math when I do concentration versus time? I'm asking it, are you zero order? And the answer is it linear? Now, I know without blowing it up, that kind of looks linear, but that does have a curve to it. Remember, if you have a graph, if you're the one making the graph, you can blow it up. You can change the axis, something, make sure that it's linear or curved. And so this one is curved, and so the big answer is no, I'm not zero. And so I graphed the natural log of concentration versus time. And so what am I asking it? Are you first order? And it's linear, so the answer is yes. Now, technically, I don't have to go on. I already know that it's first order, but I like to always check. Because, maybe there's a curve there and I just didn't notice. So here, it's 1 over the concentration versus time. And what am I asking? Are you second order? And it's curved. And so the answer is no. So this and this, they've done their purpose. So we don't need them anymore. So I'm only going to deal with the data that has been taken, the natural log of it. And I'm going to plug it in to linear regression. Now this will look a little bit different than what you use on Excel because I use a program called QuattroPro, and this was done a long time ago with an old version. But it used to put the data out in this wonderful little box. Now we're not going to go into a whole bunch of the statistics, but if my data wasn't perfect, like I have here, if my data was all over the place, I would like to know what's the confidence of that line fitting most of the data. And so there is a whole bunch of statistics that will tell us. And guess what? That pretty much means 100%. Whoa, my data matches my line 100%. I can trust it, completely. I'm just so good in the lab. Of course, this is made up data, so of course it's going to be linear. But you don't have to worry about the statistics, but know that there's statistics built in. All right, so regardless of what program you use, you're going to get the constant out. And remember, the constant is B. And you're going to get the X coefficient out, which is M. So you will always have those two after you do the linear regression from your scatter plot. Now, whatever program you're using in whatever version, it might not say constant, it might say intercept, or it might say B. Okay, you have to kind of look for the terms that go with y is equal to mx plus b. All right, so what do I know? Here's the questions that I can answer. Number 1, for letter A, do you know the order of the reaction? Yes, because it came out to be natural log of concentration versus time. I know it is first order. All right, second question. Well, can you give me the straight line equation? And the answer is yes, because I know the natural log at some time t is equal to a negative kt plus the natural log of the initial, but that's not good enough. I actually have numbers to be plugged in there. So this is y m x plus b. So I know that m is equal to a negative k, and the value I got off the chart was 0.0053. And I know that it has to be inverse time because it's first order. And I also know that B is equal to the natural log of the initial, which in this case turns out to be a negative 2.99573. One thing you're going to be very glad to hear when you are getting numbers off of graphs, we are not going to worry about significant figures. Yes, they're important. They always will be important, but that's just one more variable we don't need to play with right now. So at least take 2 digits. 3 digits would even be better. Okay, so if you're taking data from graphs, you do not have to use significant figures. I know I can hear you cheering, even though I'm not sitting there with you. Okay, so let me put all this together because I have a generic straight line equation, but I want to plug in the pieces. So the natural log of the concentration at some time t is equal to, all right, now this piece, negative k, is the same as slope. So I'm going to put in 0.00, what was it, 53 inverse seconds. Now, why is there still a negative in there? I can either plug in m before the x, or I can plug in negative kt. All right, k's are always positive. K's are always positive. So let me just solve this for you. M is a negative k, so therefore k is a negative m. So what is m? It's a negative 0.0053. So k is a positive 0.0053, and we know it's an inverse second. I can either plug this in, in right there, or I can replace both of them with the slope. Okay, the key is don't do your double negative. Don't do your double negative. All right, so the natural log at some time t is equal to a negative 0.0053 inverse seconds. T is my variable, and I can either solve for the concentration, or I can just plug in b. B is the natural log, so I'll subtract 2.99573. All right, the other piece that is very important is your units. And yes, units are so very important still, but in the log world, they get a little tricky. So when you take the log of a unit, okay, take the log of a unit, it goes into the big black hole. When you take the anti-log of it, it comes back. Yes, I know that's so technical, but we're not going to worry about all the variations. So if you take the log of a unit, it just goes away. And then when you take the anti-log, it just magically comes back. So I don't have a unit right here because I took the natural log of my initial concentration. All right, there is my straight line equation that I can use. So we've done this one, we've done that one. Ooh, what is the rate constant? Guess what? We actually solved for that one too, right here. What is the rate law? Okay, now we can plug in all the pieces. So, C, A is equal to 5 per seconds. D, the rate is equal to 0.0053 per seconds. Concentration to the first power. All right, so we can also use that equation. And what's next? The initial concentration. Okay, we want the initial concentration. Well, we know B is equal to the natural log of the initial concentration. And we also know B is a negative 2.99573. So therefore, the natural log of the concentration is a negative 2.99573. And the way to get out of a log, for natural logs, you take the e of it. You take the anti-log. So those two go away, and I need to plug that in. And remember what I told you about units? This is an anti-log, and so magically, the unit is going to come back. And this was a concentration, so the unit of molarity is just going to magically reappear. In a calculator. All right. 2.9573, and it's negative. And I'm going to take the entire log of it. And so the initial concentration was 0.050, again, sig figs. I'm just using 2, and then the unit just magically reappears. So there's my initial concentration. All right, next, initial concentration. All right, half-life. Oh, well, how can we figure out half-life? Well, there's 2 ways to do that. I could actually plug in half the initial concentration, or I can just go look up the half-life equation. And the half-life equation for first order is 0.693 divided by the rate constant, which is 0.0053 inverse seconds. And my unit is going to come out as seconds, which is what I was looking for time. So 0.692, 0.0053. And I end up with, again, not to correct sig figs, 131 seconds. So it's going to take 131 seconds for half of this to be gone. All right. The last one right here. Oh, sorry, there's 2. The last 2 are really the power of knowing these equations. Can you tell me what the concentration at 100 seconds, or if it was in minutes, 100 times, is going to be? All right, well, that begs the question, what are you combining? Concentration and time. Which equation uses concentration and time? Is it the rate law? Oh, nope, because that one compares rate and concentration. So that's not the one we need. Is it the straight line equation? That one does concentration versus time. Oh, that's the one that we need to plug in. All right, so do you know what the straight line equation is? We certainly do. So come down, what are we? Right there. So I'm going to erase. Very quickly, obviously. For so long, be pretending to erase with a stylus on a screen. Okay. All right. I wanted it 100 seconds. So if I want, and now notice I'm going to put a subscript here. I've been saying this whole time at some time t. Well, I'm asking about a very specific t. I'm asking about 100 seconds. So if I want to know the concentration at 100 seconds, I'm going to take a negative 0.0053 inverse seconds, and I'm going to multiply that by 100 seconds, and I'm going to subtract 2.9957. Okay, this second and this second goes away. And remember, that matches because this one right here doesn't have a unit, and you can't add 2 things together that have different units. So 0.0052, yep, I should have been able to do that in my head. Negative 0.53 minus 2.99573 equals the natural log at 100 seconds. Now add those 2 together. And we get a negative 3.53. Right, not done. The natural log of the concentration at 100 seconds equals that. Well, I don't want the natural log, right? I want to know what the concentration is. So to get rid of the natural log, I'm going to do that anti-log. And the concentration at 100 seconds turns out to be 0.0294, and I did an anti-log, so the unit miraculously reappears. Hey, what is the concentration at 100 seconds? It's 0.0294. I could have found that from the graph, I could have gone to 100 seconds and then worked my way up. But I have an equation that will do any time and any concentration, even if it's not on the graph. All right, so there's your concentration at 100 seconds. But I also want to know what's the rate at 100. Do you have an equation that will relate concentration, sorry, not concentration, rate and time? Okay, rate and time. Well, yeah, that's your rate law. Because if you want to know the rate at 100 seconds, well, guess what concentration you're going to plug in? The concentration at 100 seconds, and this happens to be first order. So the rate at 100 seconds is equal to 0.0053 inverse seconds times 0.0294 molarity. Aha, molarity over seconds. If we're finding a rate, the units are always concentration over time. So I have the correct units. And so now it's a matter of plug and chug. And my answer is the rate at 100 seconds is 1.56 times 10 to the negative 4 molarities per second. Oh, there's one of the example problems that I have for you. Let's recap. The first thing I need to know is, are you zero order, first order, or second order? So I graphed the data, and the one that came out linear happened to be the first order because it was natural log of concentration versus time. I then did the linear regression to find the constant and the slope. Once I knew the constant and the slope, I could find the straight line equation, and I could plug those in. Once I had the straight line equation, I could find K, the rate constant. I could find the initial concentration. Whoops, I erased that, the initial concentration. Once I know the slope and the intercept, I pretty much can find everything else. Those are tools. Those are tools, okay? The straight line equation, its whole power is that if you want to plug in a time, it will give you a concentration, or vice versa. If you want to give it a concentration, it will tell you what time or how long before that concentration will exist. That is its power. The rate law, the power is rate versus concentration. So if you know the concentration at a time, it will tell you the rate at the same time. That is its power. Okay, that's why we're using both of those two equations. One is dealing with rate and one is dealing with time, and it just depends on what you want to know. All the other pieces just fall out. The half-life, the initial concentration, but the real meat is coming up with those two equations. All right. So that's, oh, Bill, I was already there. So it's not deciding to scroll from there, yeah. All right. This was just the example of working through one of those problems. It is the exact same format and setup for the other two. You would just be using different linear equations. All right. Until next time, Jolly out.